here relation between CP and CV. Here before that, relation between CP and CV, here about CV. So what is CV? Here CV is equals to heat capacity at a constant volume, at constant V. We know already heat capacity. Now here the heat capacity C is equals to Q by delta T. Or here Q is equals to C into delta T. This is. Or here delta T is directly proportional to Q. This is. Yesterday definition of heat capacity explained. The amount of heat required to raise the temperature through 1 degree is called heat capacity. Now that heat capacity C is equals to Q by delta T, that is calculated at two different temperatures. Then C is equals to dq by dt. This is. We know the heat capacity of a system. C is equals to Q by delta T. Q is equals to C into delta T. This is the definition of heat capacity. So the heat capacity at constant volume. To get that, we know that delta H is equals to delta U plus delta N RT. Before that, here delta H is equals to delta U plus P delta V. This is. Now here P delta V is the work done. That P delta V is work done by the system or on the system. Sign conventions are there here. So here the process is carried out at a constant volume. That's why delta V is equals to 0. Then here this is the heat change at constant pressure. Whatever it here change in enthalpy heat is denoted as Q. Heat, that is, and it is delta U plus P into 0. Now here Q is equals to delta U. Now that is change in internal energy at constant volume is equals to heat. This is. So the value of heat at constant volume, we know the heat capacity C is equals to Q by delta T. Two different temperature, that heat capacity C is equals to dq by dt. Instead of this dq, we can use delta U. That's why heat capacity at constant volume, that is at constant volume Cv is equals to, we know, that is dq by dt. That dq is nothing but du by dt at a constant volume. So this is the heat capacity at constant volume. Similarly, here we want heat capacity at constant pressure. Here Cp is equals to heat capacity at a constant pressure P. This is at constant pressure. We know already here delta U is equal, delta H is equals to delta U plus P delta V. This is. So according to the your work done W is equals to minus P delta V we know, and according to thermodynamics, first law of thermodynamics, delta U is equals to Q plus W. So instead of this delta U, we can write in this expression as Q plus W plus P delta V. Now here we know already here work done is W is equals to minus P delta V. That's why Q minus P delta V plus P delta V minus P delta V and plus P delta V get cancelled. Then here we'll get Q, that is delta H, that is at constant pressure, that is P. Now here instead of QP we can take delta H. We know already heat capacity C is equals to your dq or Q divided by delta T dt. Instead of this Q we can take as your delta H or du divided by dt at constant pressure. This is. So the heat capacity at constant pressure Cp is equals to du by dt at P constant pressure, and heat capacity at constant volume is equals to your du by dt at V. This is. By using these two important relations, we can derive easily a relation between Cp and Cv. A very good important relation between Cp and Cv relation. Clear? Heat capacity at constant volume. In this manner, we can easily derive Cv value, and also heat capacity at constant pressure. In this manner, we can easily derive delta H is equals to Qp and Cp at constant pressure. Heat capacity at constant pressure is equals to this. Sorry, here this is delta H by delta T into P. This is. By using these two, we can easily derive one important derivation, that is relation between Cp and Cv. So that relation between Cp and Cv is Cp minus Cv is equals to R. This is the good relation. Now in this case always Cp is greater than Cv. Clear? Here to derive this, we want one of the most important simple enthalpy concept. That is, we know that H is equals to U plus PV. This is. By using this, we can write for ideal gas equation PV is equals to RT for 1 mole. PV is equals to nRT for n moles. So instead of this PV, here we can write nRT. That's why here H is equals to U plus nRT. This is. Instead of PV, we can write. So by using this equation, if we can differentiate the equation, enthalpy equation, with respect to T temperature, then we'll get one simple difference. So the differentiate equation 1 with respect to temperature T. That's why here d by dt of H is equals to d by dt of U plus here n and R both are constant. or for 1 mole we can take here instead this, take here n is equals to 1 mole. So we can take 1 mole inside this n, that's why R is constant R into here d by dt of T this is. Now this is, we can write dH by dt is equals to du by dt plus R into 1 it is, because d by dx of x is equals to 1. Similarly, d by dt of t is equals to 1. This is. We know already dH by dt at constant pressure, du by dt at constant volume. Already here Cp is equals to dH by dt according to heat capacity at constant pressure, and here the Cv is equals to du by dt at constant volume. Substitute those two values in this. We'll get here the Cp is equals to Cv plus R it is. This is the relation. Or we can write here the Cp minus Cv is equals to R. This is a relation between Cp and Cv. In this relation, Cp minus Cv equal to R, Cp is always greater than Cv. Now, by using this, here the Cp by Cv is equals to gamma. What it indicates? Gamma, what it indicates? Here gamma indicate the size, indicate the atomicity of gases. In chemical bonding explained very clearly, atomicity is the number of atoms present in a molecule. Some are monoatomic gases are there, monoatomic, diatomic, triatomic, and so on, polyatomic molecule gases. So the monoatomic gases means its atomicity is equals to 1. Diatomic means atomicity is equals to 2. Tri means 3. Poly means more than 2, 3 like. So by using this value, gamma value, we can indicate the given gas is what type of gas. Is it a monoatomic or diatomic or triatomic? In chemical bonding, the variety shapes and examples are there here. Here, monoatomic means noble gases. Diatomic means here O2, N2, CO like. Triatomic means here O3, ozone, SO2, CO2 like triatomic, polyatomic and so on. So based on this simple concept, we will create some values, we will create one table. Just observe it. Either in physics or in chemistry, based on this, they'll ask some questions. They'll give the gamma value, identify is it what type. Or while doing problems, it is a monoatomic gas, atomicity is 1, then gamma value is easy to identify. For that, I'll create one important table, simple important table. Cp by Cv is equals to gamma table I will create here. Now here the type of gas. Here it is the value of Cp, value of Cv, and here the Cp by Cv is equals to gamma. This is one important table. This table is very, very important. While doing some problems, the value of gamma we want. So here the first one is monoatomic gases. Monoatomic gases means here helium, neon, argon, krypton, xenon. Now here monoatomic atomicity of the such a gas is equal to 1. Its value is 5R by 2. R is gas constant ratio. It is 3R by 2. Then this is 5R by 2 whole divided by 3R by 2. Here 2 get cancelled, RR get cancelled. That is 5 by 3. That is equals to 1.66. This is the value of gamma for all types of monoatomic gases. If it is a diatomic, particularly in this diatomic, also we can use polyatomic linear shape molecules. So the linear shape molecule means here examples for this linear shape examples I'll write here. O2 is a linear in shape. Here N2 is a linear shape. Poly, two atoms are there. Carbon monoxide, that is say triple bond, coordinate bond like. These are the diatomic and poly and linear in shape. Linear means your bond angle is 180. So in such cases, Cp value is here 7R by 2. This is 5R by 2. This is 7R by 2 whole divided by 5R by 2. Get cancelled. That is 7 by 5. That is equals to 1.40 value. So other than this diatomic, all polyatomic, either a tri or a tetra, polyatomic, non-linear. Shape is not a linear, non-linear. Examples are here SO2, O3, ozone, like tri or poly. This value is here, Cp value is here 4R and here 3R. This is 4R by 3R equal to 4R by 3, that is 1.33 this is. So this table is very, very important. While doing some problems or maybe in examination, they'll ask for monoatomic gases, the value of Cp by Cv or gamma is R. For diatomic, or this case is important, polyatomic linear, polyatomic non-linear examples. Very, very important. Cp by Cv values. Okay, based on this, I'll explain now some important problems, previous year's problems. Before that, just I'll complete thermochemistry parts. Thermodynamics successfully completed. In thermodynamics, some important derivations, formulae, and some important definitions introduced, derived some important derivations. And finally, heat capacity completed. Next thing is thermochemistry parts. In thermochemistry part also, so many different reactions are there. So many different definitions are there. I'll introduce all definitions. Then I'll explain some important problems based on both dynamics and chemistry, thermodynamics and thermochemistry. We'll cover it maximum. chemical thermodynamics. And this thermochemistry. And this thermochemistry, thermochemical equation or equations. Thermochemical equation or equations are the reactions under thermochemistry parts. So the thermo means heat. Chemical reactions we know. It contains reactants and products. During a chemical process, like some amount of substances from initial state to the final state, there is some small change in their heat energy. Thermo means heat. So the thermochemical equations are the reactions in which heat or energy evolved or absorbed in addition to physical state, of participant are here substances and number of moles of the respective substances. So the thermochemical equations are the reactions or the equations in which amount of heat is or energy is evolved or absorbed in addition to the physical state of participants or substances and number of moles of the respective substances. Generally, chemical reaction is denoted by an arrow like this, arrow mark like this. These are the participants. Participants are called reactants. And after participation during chemical changes, during a chemical process, there is change in their heat or energy. While giving a new products, there are new substances, that is called a product. So the reactants can be converted into products. Now while converting reactants to products, here heat is some cases evolved, some cases absorbed. Now here the heat is evolved or absorbed, and also it indicates the physical state. Reactants are in solid state or liquid state or gaseous states. Products are the solid state or liquid state or gaseous state. Now this heat we know already denoted in different ways, Q or the H, U, different ways. Here we can use in terms of enthalpy. That enthalpy is H, heat content. Initial state enthalpy is H1 and final state enthalpy is H2. Product is HP, reactant is HR. Now in chemical process we can use it is a reactants, that is HR, enthalpy of the reactants. The system contains its total heat content of the system, and here products contains HP, total heat content of the system. So during this process there is a change in their heat evolved or absorbed. That change is denoted by a symbol delta or D in their total heat content. That's why delta H is equals to HP minus HR in chemical process. In physical process, delta H is equals to H2 minus HR. This reaction is called a thermochemical equation, energy equation. Very, very important. This is called a thermochemical energy equation. That thermochemical energy equation is delta H is equals to HP minus HR. By using the simple analysis, simple explanation, we can create so many different definitions based on the simple analysis. Remember here the thermochemical equations are the type of equations in which amount of heat is evolved or absorbed during a chemical process in addition to a physical state of participant or substances, and a number of moles of the